Welcome to CMB327, Chapter 8. We're covering binary mass transport with both diffusion and advection. And this is example 17. We're going to look at mass transfer in a falling liquid film. The first video here is going to derive the governing equation. So our system is a thin film of water flowing over a fin. And at the top of the fin, where z equals 0, the water is completely free of oxygen. And as it flows down the fin, oxygen enters the water from the free surface. Oxygen is also accumulating at the bottom of the fin because the water is flowing down, bringing oxygen downwards through advection. So there's both diffusion in the y direction and advection in the z direction. There's not any concentration gradient in the x direction, so we won't be looking at that in this problem. We're asked to write an expression for the concentration of oxygen in the film as a function of position. So we need a concentration profile, which means we're going to have to write a governing equation. And we've already seen that the concentration of species A, the oxygen, is dependent only on the z and y coordinates. We'll assume that the film is operating at steady state. So our first boundary condition is at the very top surface of the film. This is given in the problem, and it says that for z equal to 0, any position y, we have no oxygen in the water, so the concentration of oxygen is 0. For our next boundary condition, we look at the free surface of the film, and at any point along the free surface, so any value of z, we know that the concentration of oxygen in the atmosphere is constant, a value of Ca0. So we write that for all values of z and y equal to 0, concentration is Ca0. For our last boundary condition, we look at that solid interface between the liquid and fin, and we know that there can't be any appreciable flux of oxygen into the metal. Sure, a small amount, but it's not significant. And so we can say that there's no flux. That's an insulating boundary condition at that position. So at y equal delta and all positions of z, there is no flux of oxygen at that interface. So to start the problem, we write a differential shell balance, and we have differential units in the delta y and delta z directions because we're trying to solve for those dimensions, but the dimension in the long dimension, the width, is to derive our governing equation, we'll write the differential shell balance, and our differential shell has differential sides in the delta y direction and delta z directions because those are the dimensions in which we want to create an equation. X is not varying in this problem, so we'll just give the full width of the To derive the governing differential equation, we'll construct a differential shell balance. And our differential shell has infinitesimal dimensions in the y and z directions because we're trying to create an equation. Oh my God. To construct our governing equation, we need to use a differential shell balance. Our differential shell is going to have infinitesimal delta units in the y and z directions because those are varying with To construct our governing equation, we're going to use a differential shell balance. Our differential shell will have differential dimensions in the y and z directions because those are the directions in which concentration varies. The x dimension, which has a long width w, is not going to vary infinitesimally because there's no concentration dependence on the x dimension. So here's our unit, and we know that there's a flux of oxygen from the oxygen-rich interface through the thickness of the film. So we've got a diffusive flux, which we write as JA. We also know that oxygen is going to be both fluxing and advecting in the vertical direction due to the flow of water. And so we'll write that total flux as CAVA at C and CAVA at Z plus delta Z. And that includes both advection and diffusion. So to put this into mathematical terms, we multiply our diffusive flux by the cross-sectional area that is orthogonal to that diffusion, which is the width times the delta Z dimension. And then we write our advective plus diffusive flux times the cross-sectional area orthogonal to that vertical flux, which is again the width, but this time times delta Y. And all of this equals to 0 because our system is at steady state. So we can divide both sides by W delta Z delta Y, and that leaves us with something that starts to look like two distinct derivatives. If we take the limit as both delta Z and delta Y go to 0, we obtain the governing differential equation, which requires a little bit more simplification. So the first thing we can do is replace JAY with Fick's law. And when we do that, we make the assumption that DAB is constant, and we can simplify that left-hand side term. But we still need to write CAVA in terms of the z direction velocity that we're given in the problem. And that takes a little bit more work. So we'll start with the definition that the total concentration times velocity star is the sum of the individual contributions. And we can then rewrite CAVA as the difference between CV star and CBVB. So we've got a way of writing CAVA, but now we need to relate that to the density and velocity that we're given. So we multiply it by the molar average molecular weight of the system. So that's sort of an average. So that's the mole average of both A and B components. And when we do that, we obtain the mass flux. And the mass flux is written as rho V. And in this case, the total velocity is the velocity that we're actually given, Vz. So we can just write rho Vz. So we have a relationship between V star and Vz. And we see that it's given by this relationship between rho and the total average molecular weight. And that quotient is actually the total concentration of the system. So for this problem, CV star equals CVZ. If we plug that into our definition on the right-hand side, we have to make the assumption that the velocity of B species, which is water, is roughly the same as the velocity of the total system, because the contribution from oxygen is going to be very, very small because there's not much oxygen in the water. So it's a good approximation. And as soon as we make that assumption, we're able to factor out the VZ and C, rewrite the expression in terms of 1 minus the mole fraction of B, which of course is just the mole fraction of A in a binary system. And the mole fraction of A times the total concentration is just the concentration of A. So we're able to write that CAVA can actually be approximated as CAVZ. And this helps us simplify our equation, because we can plug that in and we recognize that VZ doesn't really depend strongly on the z direction, because we're neglecting the effect that oxygen diffusion is having on the total velocity of the oxygen water mixture. And so if we neglect that, we can take the VZ out of parentheses and we have our dimensional governing differential equation. So thank you for listening. In the next series, we'll solve this.